The combustion of propane or C₃H₈ produces 2,220 kilojoules of energy per mole of propane consumed. What mass in grams of propane will be required to heat 50 gallons of bathtub water from 35 degrees Celsius to 45 degrees Celsius if the process is 70% efficient? 1 gallon is equivalent to 3.785 liters. 1 calorie is equivalent to 4.184 joules. And the density of water is 1.00 grams per ml. And the specific heat of water is 1 calorie per gram degree Celsius. So the first step in answering this problem is to solve the mass of water. So in the problem, we are given here 50 gallons of bathtub water. And from the problem, we know that 1 gallon is equivalent to 3.785 liters. So 1 gallon is equivalent to 3.785 liters. So the gallons will cancel out. And then next, we convert liters into ml. So we know that 1 liter is equivalent to 1,000 ml. So liters cancel out. And finally, we are given the density of water, which is 1 gram per ml. So that means for every 1 ml of water, that's equivalent to 1 gram of water. So the mLs would cancel out. And if you solve the mass of water, so that's 50 times 3.785 divided by 1 times 1,000 divided by 1 times 1 divided by 1, that is equal to 1,89250 grams of water. So don't be shocked if the value is too large. Remember, this is a bathtub of water. So you expect a great or a large mass of water. Okay? So now that you have the mass of water, next thing you need to do is to solve for the heat required to heat that amount of water from 35 degrees Celsius to 45 degrees Celsius. And the formula we're going to use for that is, of course, Q is equal to MC delta T. So Q stands for the heat, M stands for the mass, C stands for the specific heat, and delta T stands for the change in temperature. So we already know the mass. That is 189,250 grams times the specific heat capacity of water is given in the problem. That's 1 calorie. 1 cal per gram degree Celsius times the change in temperature. So remember, change in temperature is final temperature minus initial temperature. So our final temperature is 45. Our initial temperature is 35 degrees Celsius. So 45 minus 35, that's 10 degrees Celsius. So if you solve this, so 189,250 times 1 times 10, that is equal to 189,2500. And let's look at the units. The grams will cancel, the Celsius would cancel, so the unit would be calories. Okay, so we have 1892500 calories. So we need this amount of heat to increase the temperature of bathtub water from 35 degrees Celsius to 45 degrees Celsius. So in the problem, it says here that 1 calorie is 4.184 joules. So we can actually convert this. So 1 calorie is equivalent to 4.184 joules. So the calories would cancel out. And you can also convert joules into kilojoules. So we know that 1 kilojoule is equivalent to 1,000 joules. So the joules would cancel out. So if you solve this, so 1892500 times 4.184 divided by 1,000, that is equal to 7918.22 kilojoules. So you need this much heat. You need this to heat up the bathtub water. But if you read the problem, it says here that the process has an efficiency of 70%. If you can recall the formula for efficiency, efficiency is equal to your heat output divided by your heat input times 100. And the efficiency is 70%. So 70, that's equal to your Q output. Your output is the amount of heat that is required to heat up the bathtub. So that is your output, 7918.22 kilojoules divided by your Q input times 100. Okay, so what you can do is you can divide both sides of the equation by 100. So the 100 would cancel on the right side. So let's continue the calculation. Okay, so let's continue the calculation here. So on the right side, what's left is 7918.22 kilojoules over Q input. And on the left side, you have 70 divided by 100, that's 0.7. And then you cross multiply. You multiply Q input with 0.7. So 0.7 times Q input, that's equal to 7918.22 kilojoules. So to solve for Q input, you just divide both sides of the equation by 0.7. So Q input, if you solve this in your calculator, this is equal to 11311.74286 kilojoules. So this is the input, your Q input. Now our Q input, let's just rewrite that, 11311.74286 kilojoules. So we need this much of heat from the combustion of propane. And we know that the combustion of propane produces 2,220 kilojoules of heat upon combusting 1 mole of propane. So as you can see, the kilojoules cancel out. And now we can convert the moles of propane into the grams of propane. So how do we do that? We simply use the molar mass of propane. So 1 mole of C₃H₈. So you can compute this using your periodic table of elements. So 3 carbons and 8 hydrogens. So the molar mass of propane is 44.094 grams per mole of propane. So the moles of propane would cancel out, and finally we have here grams of propane. So all you have to do now is grab your calculator and solve for the grams of propane. So that's 113.11.74286 times 44.094 divided by 2220. You will get approximately 224.68 kilojoules, or you can simply round this to approximately 220, not kilojoules, sorry. That would be 224.68 grams of propane. Or you can round this to approximately 225 grams of propane. So the answer to this question is 225 grams.